Welcome to the second week of the course. During this week we are going to learn the mathematical model of quantum computing, which will allow us to understand and design quantum algorithms without any background in quantum mechanics or of physical implementation of quantum hardware. Understanding of this week's material is crucially important for understanding all other modules of the course. So probably this is the most significant week in the whole course. I strongly advise you to do all the exercises for this week, and if you don't understand something, you can always ask a question on the forum thread dedicated to this week. So let's go. The most significant basic part of the whole theory of quantum computing is qubit, which is short for quantum bit. The minimal unit of information, of quantum information. And just like as one bit describes the state of the simplest classical system, like the Silver's engine here, one qubit describes the state of the minimal quantum system. And as you remember, in the Silver's engine, one bit was coded by a camera in which one molecule of gas resides, so the part of the camera. If the left part we called 0 and the right part we called 1. Just the same, one qubit of information can be encoded by polarization of a photon or the orbital of electron in the hydrogen atom or any other characteristic of a simple quantum system. As you probably remember from school, electromagnetic waves are transverse waves, which means that the direction of the oscillation is orthogonal to the direction of the propagation. So if wave propagates here, then oscillations can take place in this plane, which is orthogonal to the direction of propagation. And we can call the vertical oscillations. We can assign value 1, and for the horizontal oscillations, we can assign value 0, and voila, one photon now carries one bit of information. But you may notice that in this example here, the oscillations can take place not only vertically or horizontally, but in any other possible direction on this plane. Moreover, these directions depend on bases that we choose in the space. So when we say that we assign 1 to vertical oscillations, we first need to define what is vertical in this space. And you will be absolutely right saying this, but please note that for classical systems we have exactly the same situation. For example, in the Silver's engine here, this molecule can reside in any of these points. I have actually an enormous number of possible states for this system. But we choose to distinguish only 2 of them, because it is convenient to us and we can measure these 2 states. And in classical systems, this reducing of the number of distinguished states is called digitization. And we have a very similar notion for quantum systems, which we will discuss very soon. Now it's time to give a strict mathematical definition of the term qubit. Qubit is a unitary vector in a two-dimensional Hilbert space. So here H is some Hilbert space, the number of dimensions is 2, the length of vector phi in it is 1, so phi is a qubit. Some of us may need to recall what is it a Hilbert space at all. Well, Hilbert space is a linear space over some field with a dot or inner product. And in this course we are going to discuss only the finite dimensional spaces over the field of complex numbers. So if we have two vectors in some Hilbert space of dimensionality n, here I draw them as columns. So they both have n coordinates, which are complex numbers. Then the dot product, or inner product of x and y, we will denote like this, and will be this sum xj conjugated multiplied by yj. And this definition of the dot product satisfies all the conditions for this type of products, because it has conjugate symmetry, positive definiteness, and the linearity on the second argument. So if we have x alpha y plus beta z, where y and z are vectors and alpha and beta are some scalars, then we have this alpha x y plus beta x z. Please note that sometimes the linearity on the first argument is needed for definition of the dot product, but here we will need this. Okay, now let's take a look at this notation here. This type of notation we will use to denote a vector. It is called ket, and it is a vector column. So it is a column. And this is called bra, and this is the transposed column. Let's take it for x again. This is a transposed column, so it is a row of conjugated coordinates. And now we can understand this notation for the dot product. So here we have bra for x, and here we have ket for y, and it is row of conjugates multiplied by a column. And it is just a simple matrix multiplication, which gives us this sum, which gives us one scalar. So just a number. Now, the advantage of having this dot product of two vectors is the possibility to define the angles in the space. You probably remember that for Euclidean space, this expression the dot product of two vectors divided by the length is the cosine of angle between these two vectors. And if we will try to define the angles in the Hilbert space over the complex numbers, then it might happen then this dot product is a complex number, and we don't want complex cosines, so we are going to place the absolute value or modulo here to define the cosine of an angle between two vectors. And since in Euclidean spaces we didn't have this absolute value, we could have there the negative cosines. So the angles in Euclidean spaces vary from 0 to p. Here we placed this absolute value to avoid complex cosines. And now we also avoided the negative cosines. So in our spaces here, all angles vary only from 0 to pi divided by 2. So there's no obtuse angles there. And since we are going to discuss only the unitary vectors, which have length 1, we are going to remove this expression here. So the cosine of the angle between two qubits will be the absolute value of the dot product of these qubits. Okay, this will allow us to define which angles are orthogonal. X is orthogonal to y if and only if the dot product of x and y is 0. Now, why we use only unitary vectors? Actually, for the state of a quantum system, mathematically beta corresponds a direction in the Hilbert space, or a ray. But ray is an infinite class of vectors, which differ only with their length. And manipulating with these infinite classes is not very convenient, so we choose to choose a representative of each class. And it's very natural to choose this representative to have the length 1. Well, now we have this notion of the orthogonal vectors, which allows us to define the orthonormal basis in this Hilbert space, like this. Here we have this vertical vector, which we will call 1, and the horizontal vector, which we call 0, and the columns for this will be 0, 1, and 1, 0, and 0, 1. These vectors are, of course, orthogonal. They are unitary, so they form the orthonormal basis in our space. They are depicted here on this picture, and actually this picture is not good enough because each axis here represents a complex plane, and to draw it right I would need to draw a 4-dimensional picture, and I was not provided with a 4-dimensional tablet yet. And this unitary circle here is the all possible values of one qubit. So you can see that one qubit can be not only these vectors 1 and 0, which we denoted this way to make the connection with the values of classical bit, but it can be any vector on this unitary circle, like vector phi here, which equals to alpha 0 plus beta 1, alpha and beta both are complex numbers. So we can see that qubit can have much more values than just ordinary bit. Actually, it can have any of these infinite number of values. And this is what we already have seen before for the polarization of a photon, since we discussed that the vertical polarization we can denote as 1 and the horizontal is 0, but we can also have many other different polarizations like this, and where it leads us, let's see in the next episode.